Thank you very much for being here. My name is Hugo Brunie. I'm working here for 10 months now. I'm a NERSC-NISA postdoc working in collaboration with CRD on mixed precision for HPC applications. My CRD supervisor is Kostin Yankou, and I'm working mainly with Brandon Cook from NERSC. So, why doing mixed precision tuning? One of the success stories of the last years is the Deep Learning for Climate Golden Bell of 2018, which was won by, in part, some of the NERSC people. And they hand-tuned these codes doing mixed precision tuning, and they managed to reach, for the first time, the exaflop peak. So what was the secret of their optimization? It was, in part, the use of these tensor cores, which are in themselves doing a mixed precision operation, because the product is done in single precision, half precision, sorry, and the accumulation is done in single precision. Many other applications can actually benefit from mixed precision tuning. The problem for some other applications is that they may not be able to benefit from tensor cores, because tensor cores are specific to a matrix multiply operation. But there are some other expensive operations, like exponential, for example, and benchmarking them, we can show that there is an incentive of speeding up the application by doing it in single precision instead of double precision. There are some other incentives, like the fact that you reduce the memory footprint by reducing the precision. If you do single precision instead of double precision, you use half of the bits, and so you use half of the memory. So half of the memory bandwidth, less energy consumption. It's great. The problem is, if you do everything in single precision, you can actually break the stability and the accuracy of the code you're running. That's why in most of the cases, people use the highest precision available, which is double precision. Okay, so mixed precision tuning is important. Now, what it is actually? What is this? How do we do this in practice? For each of the operations of your program, you can decide between, say, two types of precision, single precision and double precision. And choosing this for each of the operations will actually define what we call a type configuration. So for each operation of your program, you map a type which is single or double precision to this operation. And what we see here is that if you make this choice for each of the operations of your program, the search space grows exponentially with the number of operations. So that brings to the limits of the current practice. The current state-of-the-art tool trying to search this space is actually non-scalable. That's why we focused on work on trying to develop a scalable method. Our method must also be automatic to be user-friendly, to make the end user able to use it. We also decided to target the hotspots to actually be able to improve the performance of the application. Thus, we focused on math function calls from the dynamic math library because of several key points. The first point is we want our method to be scalable, so focusing on math function calls, we actually reduced the search space, because in a program there are less math function calls than variable definitions. These math function calls are also used in many science applications, so it's interesting to have such an optimization. Finally, they are expensive, so they are mainly in hotspots of the application. And the last point, but not the least, is that they are called by dynamic library, so we can intercept these calls and make an automatic tool. So now I will illustrate some of these points. The first key point is the number of elements in the search space. Say here you have two math function calls, the two first levels of the trees, and three variable declarations. If you represent your search space as a binary tree choosing between single and double precision, you can show that reducing it by removing the variable declarations, it's actually drastically reducing the search space because of this exponential growth. The second key point is the behavior of some real applications show that math function calls are actually called in hotspots because of their expensive cost in terms of cycle. Here we have profiling with VTune of a real application developed here at LBL that shows that the hotspot is in exponential calls. And actually, we can decompose this exponential in the different call sites in the source code here. So in this code, there are 9 different call sites in the source code. And for each of them, we can count the number of dynamic calls of each exponential. And intuitively, the more an exponential is called, and the greatest will be its impact on the performance. And that will be important for a heuristic. The last point, but not the least, is the dynamic library call. As the math functions are called in a dynamic library, we can actually build a tool that will intercept these calls from the program to the library and then choose between the different precision we want to use. This way, we can profile the application to know what is the difference of actually using double or single precision, and also try any type configuration we want. Now, I will show the application of this approach on 2 LBL applications. One is chemistry code, so you have certainly seen this image before. The second is maybe less known here. It's a crystallography application where they actually simulate the nanobrack spots. So in real life, you have incident radiation, like a beam in ALS, that goes on crystal. And then, depending on the crystal structure, you will actually have a different pattern of nanobrack spots, which is the image on the right. So we cannot really see the nanobrack spot, but they are there. And the idea of this application is to simulate this in order to understand what is the impact of the crystal structure on the nanobrack spots, and then to be able, in real life, when you see this kind of picture, to understand backward the structure of the crystal. So first, on this crystallography application, one of the hotspots is CUDA kernel, so running on GPU, and that calls exponential in the hotspot of the CUDA kernel. And if you actually untune this exponential from double precision to a single precision CUDA intrinsics, you manage to gain 40% speedup on this kernel. The final result impact is marginal, as we have tested many different input data, and the difference is only of 1 pixel over the 9 million pixel images. So this is quite an easy story because we have just one call site. We try to reduce the precision of this call site, and it works. The second application, I already presented you this. So just to show you that the exponential is important for the performance of this chemistry application. These calls are actually done in 2 modules. The lead wire module, which is computing the production rate of the chemistry, and the second, which is computing transport equations. Let's try the strategy as previously on the crystallography application. Let's try to do in single precision all the exponential calls. What happens? Actually, what happens is that the application crashes because the ODE solver doesn't converge on some iterations. This is understandable because the exponential calls results are all linked with all other modules, and so there is an impact of reducing the precision on the stability of the code. The question now is, we have 9 call sites, thus 512 combinations. Do we want to try them all to find a solution that have a great performance for this application? The answer is no, we don't. So what we tried is to take into account a very important necessary condition, which is that if you have a locally high error between the double precision and the single precision, this high local error will actually influence the whole code and may destroy the stability of this code. That's why our tool profile the application to understand the local, to compute the local error for each of these call sites, and then our algorithm will try to lower the call sites that have the most impact in order to highlight the one that we must not reduce. So here is our heuristic. I will then detail it on a simple example. But just basically what it does is it tries a type configuration to maximize the number of calls you do in single precision. And then, if it doesn't work, it tries a configuration that maximizes the local error in order to reduce the search space. So with an example, it's maybe more clear. Here we have 4 call sites, A, B, C, and D, with increasing local error order. That means that D has more local error than C, than B, than A. And here are the different type configurations. So a sequence of letters means how many call sites do you do in single precision. For example, here A means you just lower the precision of A. B is just of B. AB, you lower the precision of A and of B simultaneously, etc. So algorithm first tries to lower all the call sites, A, B, C, D. It doesn't work. So then it tries to lower the one that has the greatest local error impact, so D. Lowering D, it doesn't work, like the application crashes. But what does it mean? It means that you can actually remove all the type configuration that imply to lower B. And that's how we reduce the search space. Then we are greedy again and try to lower ABC. So in 3 steps, instead of the 15 combinations, we managed to find a solution for this problem. We applied this heuristic with our tool on the PDC chemistry application, and we found a solution in 3 steps. Then what we had to do is to compare the final results with the original reference results in order to understand if the science behind it is still correct. To do that, we agreed with the developers of the application that one of the main correctness criteria is to compute the flame speed. So here you have a graph that represents the flame speed on the y-axis according to the time spent.
Hugo,
yeah.
Could you
still
stand at the mic, and
okay.
You could use the mouse to point on the screen, and then the audience. There you go.
Oh yeah, thank you.
Thank you.
So here we have a graph showing the flame speed in y-axis against the time. And the idea is, with the mixed precision run and the reference run, the 2 curves goes almost perfectly on each other. So what we did is compute the relative error of the 2 curves, and we have here a curve that goes to a horizontal asymptote that converges to 5 10 - 8. As the input data of the application are significant digits between 4 and 6, this relative error is acceptable to the developer of the application. To summarize the results on this application, there is 30% of the time spent in exponential calls. So the potential speed up with 1.5 speed up on CPU is 8%. But if you try to reduce all the exponential, it crashes. By using our heuristic, we managed to find type configurations that brings 8% speed up in only 3 executions. To conclude my presentation, I will insist on the fact that floating point mixed precision optimization is important for the future because also of the evolution of the hardware. The current state of the art is limited in the search space strategy because it's not scalable. We have developed a tool that narrows the search space So we are not targeting all the applications. But narrowing this search space, we managed to make it scalable and applicable on real applications. The limits short term are a compiler dependency because of the interception of the calls. The Intel compiler, for example, changed the name of the exponential. And the GPU compatibility, we still are working on making our tool automatic for GPUs. And long-term limits, which applies to all the community doing mixed precision tuning, is the accuracy criteria research. When you develop an application, for example, the chemistry application, actually defining a criteria that says your result is correct enough and I trust it, it's a hard task and still in open research. Thank you very much. I want to thank NERSC and CRD for their collaboration for this postdoc. On NERSC side, especially Brandon Cook and Jack Deslip. And on the CRD side, I'm working with Kostin Yanku, Khaled Ibrahim, and Adia Hamed. Thank you very much for your attention. If you have any questions.
Hugo, how do you see this working for code, users of code or writers of code? Are you going to try to make it automatic, or is it a tool that helps you put in?
The idea is make it automatic, so they run the tool of their application. They let it run for some time, and in the end, it gives type configurations saying if you lower this kind of calls, so yeah, if you change your code, if you lower this kind of code, so you will have this speed up. So yeah, that's what we are.
So it will require the programmer
to change this code, because like we could also make it automatic in the sense that he doesn't have to change the code, but our tool automatically changes the codes by itself. That's what I do on the chemistry application. The thing is, I think the developers want to understand what they do to their code, and to like if they want stable changes for all the future of their iterations, like when they will change the code and whatever. I think changing the code to implement a new optimization is better. Like when you do cache blocking or vectorization, you don't use a tool that does it automatically. You actually change your code to take into account the optimization, I think.
Yeah. After the pruning, is there any possibility that different correctness measures of the code could be affected differently? Like if you had, I don't know, if you had a particle and cell code, like you had to, like momentum conservation and some other conservation, could the pruning affect those two conservation laws differently?
Can you repeat the question so that?
Yeah. So the question is, can the pruning affect the stability of the code?
Yeah, differently. Like if you have a different way to measure the correctness of the code.
Oh, I see. Yeah. Yeah. Of course. If you change the function that decide if your code is correct or not, it will obviously change the whole. It could change the result of the heuristic, because the heuristic is entirely based on this function that tells in the end if the code is correct or not. So yeah, that's why defining this function properly, having a good criteria that define if the final result is correct or not, is important. And it's actually not a trivial task. Yeah.
Thanks. Anyone else? Okay, thanks again.
Thank you.